today, we're going to talk about SD-WAN policy. And when I say SD-WAN policy, I'm talking about full-on policy as it would affect the two control planes of operation that we've been discussing. Now, today, we're not going to bite off all of it. What I plan on doing is I am going to address the two types of policy. Now, remember, I said that we have this implementation of scope. And scope actually extends to whether or not a policy is going to be deployed in a centralized fashion or whether it's going to be deployed in a localized fashion. And it becomes very important for us to realize that these two operations are going to exist for each of my constructs. So I'm going to have I have the possibility of having a centralized data plane policy. I can have a centralized control plane policy. I can have a localized data policy, and I can have a localized control plane policy. And what we want to start doing is kind of mind mapping those out for the purposes of being able to visualize the functionality and the capability of each and what they do for me. However, I'm only going to go down the centralized policy in today's session. We will highlight what they are. So first of all, we have this concept of what we refer to as a centralized policy. And we have the concept of a localized policy. I'm going to go ahead and just write policy in here so we know exactly what we're talking about. So I have localized policy and I have centralized policy. Now, I'm going to treat these differently from the perspective of the way we're going to approach them. So today, what we're going to do is we're going to explore centralized policy. Now, that means specifically both centralized data and centralized control plane policies. In the next session, what we're going to do is we're going to talk about localized policies. But what I want to highlight right now out of the gate is pretty much what these categories are. So when we start looking at a centralized policy, it becomes important for us to understand that we create a centralized policy in order to affect a whole fabric. So I want to write something that's going to affect the whole overlay fabric. I'm trying to be as specific as possible here so that we all have an understanding of what it is we're describing. So the effect here is I want to use a centralized policy, whether it's a data policy or control plane policy, in order to affect the whole overlay fabric. Now, there's only one device and only one resource in the entire infrastructure that can perceive the whole overlay fabric, and that's going to end up being my Vsmarts. And that's an important observation that we need to keep in mind. So what I'm going to do is I'm going to go ahead and containerize this because this is going to be the fork in the road that we're going to explore. When we get back together again in our next session, what I want us to note here is that we're going to be talking about localized policies, and a localized policy is going to affect a single device. So it's not going to be everywhere. So in other words, if I want to do something in a targeted fashion, I'll leverage a localized policy that can affect control plane, or it could affect data plane, or I could write policies that could do both. But like I said, we're going to highlight and we're going to branch that out moving forward in our next session. So we've already mentioned the fact that for each one of these outcomes, for each one of these forks in the road, whether it's centralized or whether it's localized, they're going to break down into two primary types of policies. The first is going to end up being our control plane policy. And then the second is going to be our data plane policy. Actually, again, I'll write out the policies. So again, we know exactly what it is we're talking about. Now, what's the difference between control plane policies versus data plane policies? Well, control plane policies are written in order to be able to affect OMP, which is why I stress the fact that we want to understand how OMP works and the fact that there are multiple types of OMP routes. Specifically, a control plane policy is going to be utilized to affect the idea of OMP routes. Remember, we called those V routes. So I'll just write V route here. And it's also configured in order to be able to impact the advertisement. I'll say T-lock advertisement, or as my other mentor would say, advertisement. So that's what a control plane policy is built to do. It is designed to affect the OMP routes, meaning V routes, which again are going to be IP prefixes that correspond to T-locks. And again, a T-lock is going to be a value that is going to be a combination of three pieces of information. Remember, that's going to be our system IP of the device, plus the color that has been assigned to the transport infrastructure, gold, silver, MPLS, private 1, internet, well, business internet, public internet, custom 1, 2, 3, or 4, plus the encapsulation type, which by default is going to be IPsec, unless I selectively change it to GRE, which again, I hardly ever see ever done other than just to be able to gather information and send it via GRE tunnel to a ER span collector like Wireshark. Something that can run ER span, encapsulated, routed, switch port analysis. Now, when it comes to data policies also have a purpose in life. And a data policy is designed specifically to actually directly. So I can affect data decisions indirectly using a control plane policy. And in fact, what I'm going to write that in here. I can use this to indirectly impact the data plane. So if I forbid two devices to form an adjacency by filtering out the adjacency state mechanisms, obviously data can't travel across that link if it can't form. So I can indirectly impact the data plane. However, a data plane policy is specifically and intently designed to directly affect forwarding. But specifically, what it is that I'm trying to affect the forwarding of. Well, I threw my stylus across the room. I'm trying to directly affect the forwarding of packets. And obviously, what this translates to is I am using this policy to directly affect the data plane. So these are our two categories of policies. So we have control plane policies and we have localized policies. Now, it doesn't end there. Like I said, it's too much to bite off in one big chunk when it comes to trying to look at each of these things. But understand that the rule of the land here is that I'm either going to affect the entire fabric, aka the overlay, or I'm going to affect individual devices that are a part of that fabric. Centralized, the overlay fabric, versus localized, singular individual devices or groups of devices, selective individuals, not all at once. And it also needs to be said that there are ways of being able to leverage a centralized policy to be a little bit more selective, but out of the box, they're designed to impact the entire overlay fabric. So what I'm going to do is I'm going to highlight that, because to me, that's probably the most important thing that we need to keep in mind. And that is the fact that a centralized policy is designed to affect the overlay of the entire fabric, and a localized policy is designed to impact a single device, but it could be groups of single devices. So again, it's not all or nothing or mutually exclusive. And again, I can have both of these constructs. Now, when we began our conversation, I was talking about the fact that when it comes to centralized policies, the only device that we have in our infrastructure that has a perception or a knowledge of everything in the infrastructure is a Vsmart, which is one of the reasons a lot of times you'll actually hear these centralized policies referred to as Vsmart policies, especially in a lot of the older documentation. So Vsmart policies are policies that are written to affect the whole overlay fabric, and I can utilize them to directly affect OMP routes and TLOC advertisements. Ergo, I get the ability to be able to directly impact the data, indirectly impact the data plane. Where when it comes to a data plane policy, again, I'm directly affecting the forwarding packets themselves, the actual bits of information that's being exchanged in the environment. And again, this allows me to directly affect the data plane. So either way, I'm still affecting or impacting or implementing or communicating to the actual data plane. Now, when it comes to control plane policies, the things that we need to understand is that they're going to be control plane policies. They're designed to affect the OMP routes and the TLOC advertisements, as I've mentioned, but they are fundamentally going to be broken up into two primary types. So when it comes to control plane policies, there are two primary types, and the two primary types that we're going to need to discuss is going to be the first one, which is going to be the idea of a topology policy, and then the second is going to be the idea of what we call a VPN membership policy. So why would I have a topology policy versus a VPN membership policy? What do they do for us, and how do we apply these, or why would we apply these? Well, when we start looking at the idea of a topology policy, that's the tool that's going to allow me to be able to exercise control over OMP routes and TLOC advertisements. Now, students at this time say, Terry, well, you just said that a control plane policy is designed to affect OMP routes and TLOC advertisements, ergo giving you the ability to indirectly impact the data plane. And if that's what topology policies do, why do I have another type of VPN or another type of policy, excuse me? So what I'm going to do is I'm going to highlight this one. Because like I said, we have a topology policy that controls OMP routes. Let me fix that misspelling there. OMP routes and TLOC advertisement. Well, then what does a VPN membership do? Well, what a VPN membership does is a VPN membership gives me the ability to be able to instantiate some level of selectivity. I'll just write in selectivity. Now, what do I mean by selectivity? Well, understand that when I have a device, so let's say we have vEdge 21. And vEdge 21, right now, we know that vEdge 21 is going to be divided into a VPN 0 set of interfaces that might go out towards multiple transits. So let's say this one goes out to MPLS. This one goes out to, say, for instance, the business internet. So we know that we have VPN 0, which is a way of being able to say, hey, this device is actually going to have a routing information base that's going to correspond to this VPN. And as I've said 100 times, that's going to correspond to my global routing table. So whatever routes are in that routing table. But this is also going to possibly be subdivided into some other VPNs. So as an example, we know that we also have the idea of a VPN 512, our management VPN. So we've got VPN 512 here. Remember, VPN 0 and VPN 512 cannot be deleted. But what about these other two interfaces? Well, these other two interfaces could also be connected to resources that I still want to have macro segmented from everything else, and this might be VPN 100. I could also have the exact same scenario where this interface right here could be connected to resources that are part of VPN 200, just to cite an example. Now, when I start applying my policies, and if the only policy that I had was a topology policy, and I want to be able to control OMP routes and TLOC advertisements from the perspective of the Vsmart, we need to understand what the Vsmart is doing here. Because if I draw my Vsmart, in this specific instance, this Vsmart that we're going to have in our infrastructure is actually going to have a series of databases that are going to be associated to the prefixes that it's learning on a VPN by VPN basis. So what I'm getting at here is that if I have a VPN of 100 and 100 knows about 4 routes, those 4 routes are going to appear here. If I have this blue VPN down here and it knows about 3 routes, and this is going to be where I have the information for VPN 200, and those 3 routes are in here, understand that it's the job of the Vsmart to gather that information from all of the devices that are advertising it, place all of that information inside of individual routing information bases that are going to be running for OMP, Overlay Management Protocol. And this data will be, in its very nature, isolated from each other just based on the fact that a VPN is the equivalent of a VRF. And when we start looking at this, if I were to write a policy, let's say I dictate a topology, and I say, okay, I want to create and enforce a specific topology type. So as an example, I want a hub and spoke. So what we'll do is let's go ahead and say I have an ISP connection. I have vEdge 1. I have vEdge 2. And I have vEdge 3. And let's go ahead and say that vEdge 1 is my headquarters. We'll say vEdge 2 is a branch. We'll just say branch 1. And vEdge 3 is going to be branch 2. And if I wanted to create a policy that was going to implement a hub and spoke, I wanted something similar to what DMVPN would do. So this would be my hub, and this would be a spoke, and this would be a spoke. Well, now data can't travel spoke to spoke because what I've done is I've dictated a policy that says otherwise. However, if I do not have a selectivity mechanism, the assumption here is I'm going to do that for all VPNs. But what if I only wanted to do that for VPN 100? What if it was traffic that was in VPN 100 that I wanted to subject to something like an ASA sitting out here or some kind of firewall, Palo, whatever, I don't care. And I don't want data traveling from spoke to spoke unless it's been exposed or run through whatever my security appliance is. Well, then the assumption here is that if I have only the ability to be able to dictate the policy with no selectivity, what ends up happening is I cannot do this other than on or off. So by having this second type of policy, what this is going to do is this is going to give me the ability of being able or the ability to be able to implement this in a more granular fashion. So the object of the exercise here is to recognize that what we're going to do is we're going to use the VPN membership to control the distribution. Specifically, I'm going to use it to control the distribution of routes learned from, so let's say the distribution of routes from particular VPNs to affected sites. Now, again, some people get really confused by this. But again, if you think of it in the terms of what I was describing, understand that if I only said that I could have a hub and spoke topology, and I can't do this on a VPN by VPN basis. In other words, I'm going to have a hub and spoke topology for both VPN 100 and VPN 200. And it also is going to have to be understood that we also might want to do some additional filtering. So if we looked at what's happening here, let's talk about how I would implement a policy like this. So we have vEdge 1 and we have vEdge 2. And let's go ahead and say that vEdge 1 has an interface, and that interface is going to be in VPN 100. VPN 100 is also going to exist on an interface on vEdge 2. And let's go ahead and say that vEdge 2 in this particular instance is going to have 1.1.1.1/32. And we're going to say that vEdge 2 is going to have 2.2.2.2/32. And what I'm also going to do is I'm going to have a headquarters router out here. So I'm just going to call this headquarters. I don't really care too much about it right now. But it also is going to have VPN 100. Now, let's operate under the assumption that this guy's got 9.9.9.9/32. And just for the sake of conversation, let's operate under the assumption that all of these devices are only connected to a single transport. We'll say MPLS. Now, we know that the way this is going to work is these devices are going to be bifurcated such that they are going to have interfaces that are going to be in VPN0. And it's going to be connected to MPLS. This guy is going to have the same situation. He's going to have an interface that is going to be connected to MPLS, and it is going to be in VPN0. And I just arbitrarily picked MPLS. It doesn't have to be MPLS. And we also know that this device is going to have an interface that is going to be connected to MPLS, and it also is going to be in VPN0. We also know, based on what we've described, is every one of these interfaces or every one of these devices has a point of presence into VPN 100. Ergo, we know that at the end of the day, these devices are going to exchange routes with each other. And if I leave everything as is, what I'm going to do is we are going to, remember, have our Vsmart sitting out here. And because we only have one Vsmart to talk about, and because we only have one active VPN, that means that we're only going to have to keep track of one VPN with regard to what we would refer to as our OMP RIB, our routing information base. And remember, this is all OMP prefixes. So now I got to give these guys a site ID, or system IP, I'm sorry. So we'll go ahead and give this guy right here 10.1.1.9/32. We'll give this guy right here a 10.1.1.1/32. And we'll give this guy right here a 10.1.1.2/32. And I'm just symbolizing those as our host routes, when all actual fact we know that these are all just numbers. But the system will create a system interface in a vEdge and employ it for communication. So what we've got is we have our overlay now. But how do we get that overlay? Well, remember what's going to happen is this guy right here is going to report, and it's going to say, well, 9.9.9.9/32 is going to be reachable via my system IP. So I'm not going to write all of these out. So what I'm going to do is just, I'm going to annotate this as HQ. So it's going to be reachable via the HQ's HQ system IP plus MPLS plus IPsec. I don't want to have to write out all the IPAs over and over and over and over. It's also going to learn that 1.1.1.1/32 is going to be reachable. We'll call this branch 1, and we'll call this guy branch 2. And again, I'm just using shorthand here to try to simplify all of the writing and not to clutter the screen. But this guy's going to say, okay, well, this prefix is being advertised by branch 1 plus MPLS plus IPsec. And we're also learning that 2.2.2.2.2/32 is going to be reachable at BR2 plus MPLS plus IPsec. And remember, these are TLOCs. And remember, we also have a TLOC routing information base on a resource by resource basis that's going to translate to WAN IPs. So in other words, ultimately I'm going to know I'm going to be able to reach 1.1.1.1/32 by sending data to branch 1's VPN 0 interface pointing to MPLS. It's IP. It's public or private WAN IP address. And we also know that because of OMP, this device is going to learn about 9.9.9.9/32. He's also going to learn about 2.2.2.2.2/32. And the same thing's going to happen over here. I'm going to learn about 1.1.1.1/32 and 9.9.9.9/32 by default. Same thing up here. I'm going to learn about, I've already got 9 in my table. So, because it's connected, but I'll go ahead and write it in here just so that I'll be able to point to it. /32. And I'm going to learn about 1.1.1.1/32. And then I'm going to learn about 2.2.2.2/32. Now, if I wanted to build a centralized control plane policy, that gave me the ability to be able to create a hub and spoke topology. The issue that I have here is that I already know that from this device right now, today, if I say ping 2.2.2.2 in VPN 100, we already know that this device is going to send data from here. I'll go ahead and just do it in a orange. It's going to form an IPsec tunnel that's going to allow data to go from here to here. I also know that headquarters can go from here to here and from here to here. So what we have here is an arbitrary full mesh infrastructure, which is what we get by default inside of SD-WAN. And if I had more than one transport, I would actually be able to have a full mesh through all of them. And that's what happens by default. But in this situation, I don't want to do that. I want to implement a hub and spoke architecture. But I want to impact or manipulate or affect the control plane to accomplish that task. And I am going to write policy that is going to impact the Vsmart, which is why we call these Vsmart policies all the time. So how could I do this? Well, we've got a number of things that we can pay attention to here. So what I could do is I could write a policy that says that if I am learning about an IP address or a route, I'll just say a route from a branch device, I want to allow that to be advertised to my hub devices. Because remember, my hubs would have to resolve all reachable addresses, just like what I have here. But what if I also wrote a policy that said that routes from branches, that shouldn't be branch one, that should be just branches in general. So what if I write a policy that says any prefixes learned from a branch do not advertise to other branches? So what just happened? So if the Vsmart is learning prefixes from branch offices, how is this going to modify my behavior? So what we're going to do here is this is going to be pre-policy. This will be post-policy. So again, pre and post. And I'm going to grab this right here. I want to try to grab that right there. I'm going to drag it over here. So this will be pre. This one will be post. So let's take care of the hub first. So our policy says that any routes learned from a branch, and again, I would use a site list to pick this behavior. So this would be like site, this would be like site 100, this would be like site 10, and this would be like site 20. And then what I would do is I would create a policy that says, that would define what I would refer to as, I'd call it branches. And inside of that branches, I would actually use a site list that would specify 10 and 20. So the system would know that branches are going to be sites 10 and 20. And then what I could do is I could create one called hub or hubs. And then I would then specify another site list, and that site list would be 100. It would just have that one in it. So I would write a policy that's going to say, oh, well, if the data is coming from 10 and 20, I know it's a branch. And then I'd write a policy that says any data that's learned from a branch could be advertised to a hub. So what that's going to result here is I'm going to have all the same prefixes, 990 slash, I'll have 1.1.1.1. I'll have 2.2.2.2 because I'm not applying any policy at the control plane level that's going to filter this information. It also becomes important to understand that I can actually apply these policies inbound, or I could apply these policies outbound of the Vsmart. Now, my policy did nothing to affect my headquarters router. My headquarters edge device is learning all the prefixes it needs to know, and it's advertising all the prefixes it needs to know. So if I take a look at what I'm doing now, and that means that I have basically followed this part of the instructions. So route from branches are going to be advertised to hubs. And there's no policy that says do not allow or do not learn hub addresses or on branch devices. So what that means is that this guy is going to know about 9.9.9.9 because I have no policy written to stop it. This guy is going to learn about 9.9.9.9. Let me move this over. So nothing stopped that behavior. However, I do have a policy here. And that policy, actually, let's use red since I'm blocking it. So let's say that policy right here is going to say, do not advertise branch information to other branch information. Well, first of all, it becomes important to note that I'm already going to know about my address, 1.1.1.1, because it's connected, and this guy's already going to know about 2.2.2.2.2. He's already connected. And my policy is now going to say this guy is not going to learn about 2, and this guy is not going to learn about 1. Well, now the issue that I have here is that these two resources, since I don't know that 1.1.1. That 2.2.2.2 is reachable from the IP address on branch 2, I can't send data to it. In fact, I don't even know it exists. However, there are a couple of things that we could do here as far as the reachability. The easiest thing to do would be to generate a default route. And if I generate that default route and I say send that information to the headquarters device, what that means is that I can send data direct to 999. So if I wanted to hit this address or anything on that address, then what I would do, that's what I would put in place, and I would be able to send data direct. But if I was going to contact anything other, specifically for our talking point, anything that's part of 2.2.2.2, well, that data would have to go to the hub. The hub would do the lookup, and then the hub would say, oh, I need to send it down to this guy. And what I just did is build a hub and spoke. And since I did that, since this device knows nothing about this device, there would never be an IPsec tunnel that could form between these two resources because they don't know about each other. However, to reach each other, they are both perfectly capable of sending data through this IPsec tunnel to the hub, and then the hub would send it through this IPsec tunnel to the destination, or vice versa. And again, this is all great, well, and good. But notice that I've said, hey, I want this topology, but bear in mind that there are inside of every one of these tunnels, I'm carrying data from multiple VPNs. So let's go ahead and say VPN 100 is yellow. But I might not want to do that for every VPN. So what I would end up doing is I would specify using a VPN membership list that would say, okay, well, let's make a hub and spoke for 100, but I have no problem with data going direct for, say, VPN 200. So I wouldn't write a policy for it. All I would do is write a control plane policy, and I would specify the VPNs that I wanted that policy to have effect with, thus giving me what I have illustrated right here. When it comes to a control plane policy, my intent is to affect OMP routes and TLOC advertisement. and I can leverage a VPN membership configuration to give me selective oversight or selective impact based on a VPN, a subset of VPNs, or I could choose to use all VPNs. So again, the object here is that this is designed out of the box to give us the ability to be able to reach out and impact what's happening in the control plane. Ergo, I can implement the equivalent of traffic engineering in the data plane by manipulating the control plane. Ergo, this is why this is always saying indirect. So I'm getting the benefit of indirect data plane manipulation by manipulating the control plane. So if two devices never know about each other, but they know about a common device, I can orchestrate the information such that data can travel from one device to this point and then to here, and then the return traffic would follow the same path on a VPN by VPN basis. So again, centralized policies affect the whole overlay fabric. A control plane, a centralized control plane policy is designed to affect OMP routes and TLOC advertisement. And I can leverage that through the granular deployment of both topology policies and VPN membership policies. Now that leaves the other part of the equation, the data plane policy. When I start looking at the data plane policy, we already said that the data plane policy is built to directly affect the forwarding of packets in the data plane. It is a direct impact solution, but it is a direct impact solution that is going to give me the capability of making decisions by manipulating the control plane. Now, again, that causes students to kind of look at me cross-eyed. And one of the tools that we have when we start looking at this, we really have 3 different methods that you guys need to know about when it comes to giving me the ability to affect the forwarding of packets in the data plane. One of the first ones is what we refer to as application-aware routing. Now, that's making a forwarding decision. So basically what I would do in an application-aware scenario, I would first of all match some category, some criteria. I could match it based on QoSMOS. I could base it matched on NBAR. I could do it based on something as simple as, say, for instance, a DSCP value like 46. So I'm matching a particular set of traffic. And then what I'm going to do is then I am going to measure. So what am I getting at? Well, I have a device, and that device is going to be running through 2 transports. Let's say I have MPLS, which normally would be faster. So what I'm going to do is I'm going to create a policy that's going to say, I want you to send data out of MPLS because it is a more direct, faster route, has an IPSLA, has quality of service and all of those other things. But I also may have a connection out to, say, for instance, a business internet connection. And I don't want to, if MPLS is down, I don't want to drop my data. So yes, I can and will send it through business internet, but as a last resort. However, in networking for decades, we have always dealt with this principle of absolutes. So if I want to load balance across a scenario, or if I want to pick another path over another, I would manipulate the control plane in, say, OSPF and say, okay, well, I'll just give this one a better cost. And if we don't do that, what ends up happening is cost is actually calculated on the basis of the bandwidth. But we assign the bandwidth as a hardware set at the interface level, and it doesn't vary. And we really can't pay attention to principles like load and packet drop and those things, because that would actually cause reconvergence. If we lose one of those criteria, we'd have reconvergence in our routing process. And again, like I said earlier, if we're reconverging, we're not forwarding. So that's one of the reasons you guys may think back to EIGRP. Remember, EIGRP used to calculate its metric. We have what we call the K values. And as part of that, we have the idea of delay. We have the idea of bandwidth. We have the idea of, well, let's just look at delay. Load is where I'm going, but load and delay are the 2 that I want to look at. So when it comes to load, we basically don't pay attention to it. In other words, how loaded is the circuit? We turn that off. We give it a K value of 0. And then delay is on, but it's hardwired. So the delay is normally going to be some value based on the speed of the interface. So again, it's hardwired. And when we configure an interface, we go in and put the bandwidth in, or we just use whatever specified on the interface because it's an Ethernet interface or a serial interface. And I know serial interfaces are few and far between now in more modern data centers and more modern enterprise deployments. But the problem with all of those things is they are static. And they are not computational, because as soon as a K value changes, EIGRP at the very minimum is going to at least do a local computation, not necessarily a topology-wide computation, and those computations are disruptive. So one of the things that we look at here is that that has always been a problem. And we've had technologies like protocol-independent route optimization, PFR in the iOS world. Before that, it was called optimized edged routing, and a number of things. And the idea that we get in SD-WAN that is the analogous to that is AAR, application aware routing. Now, what I'm talking about when I measure, I'm actually going to use bidirectional forwarding detection. Remember, we talked about the fact that for every IPsec tunnel I get, I will always have a bidirectional forwarding detection instance running in that tunnel between endpoints. It's on by default. You can't turn it off. And it will always be one-to-one. So for every IPsec tunnel I have, I will have a corresponding BFD instance that is used to generate synthetic traffic inside that tunnel to be able to take performance measurements. Measurements that I'm going to look at are going to be the things that we wanted to do in EIGRP, like latency, like load, like delay, like packet loss, all of these things. And then what I would do is I would write a policy, and my policy would actually dictate a threshold. So if my threshold says, okay, I want everything to be good to go as long as I have less than 5% packet loss. I'm just throwing out arbitrary numbers. Or let's say I have 100 milliseconds of delay. So as long as the circuit has less than 5% packet loss and 100 millisecond delay, can use it as the primary. Honor the preferred designation. However, the second that it drops below or more than 5%, or my latency jumps above 100, go ahead and send the data across business internet. Now, interestingly enough, let's go ahead and say that right now it gets moved. So the data stops going through MPLS and the data is now going through business internet. Remember, business internet is also using an IPsec tunnel. Business internet is also going to have a BFD instance. Business internet is also going to be having measurements, and since this is my application aware policy and this is going to be my application traffic that I want to provide deferential treatment to, I'm also going to be exercising my policy. So as long as the performance characteristics of business internet satisfy those of the application aware routing policy, what's going to end up happening is data will continue to go out business internet. But what if business internet all of a sudden says, okay, I've got slightly more than 5% packet loss or slightly more than 100 milliseconds of latency or delay? Well, then what's going to end up happening is because the IPsec tunnel for MPLS never went away, what's going to end up happening is the system is still running the threshold and taking measurements and doing a comparison. So the moment that they're both crap, the traffic is going to go back to MPLS because it's listed as preferred. If business internet is going to be my second preference, but at any time data is going across business internet and MPLS falls back within tolerance, the traffic will move again. So this is an unprecedented level of control and orchestration that's going to be handled by the vManage based on the application aware policy that I can implement. And it's probably the most common tool that we have in our inventory in order to be able to make decisions, in order to be able to, Cisco says approximate. I think we exceed the functionality of protocols like Pyro or PFR or OER, depending on how long you've been doing this. So again, the features change mildly, but the names change and periodically. I mean, for the longest time, it was very difficult to keep track of everything. I mean, what we call IPSLA now used to be network assurance responder. I mean, it's the same technology, it just has different names. So when it comes to application-aware routing is actually affecting the actual data path based on performance characteristics associated with that data path as compared to a threshold that we create, which is actually going to be the policy. And again, this is deployed on the basis of specific characteristics, like, for instance, does it match a particular network-based application recognition tool like Cosmos inside of a vEdge or MBAR2 inside of a cEdge, or is it based on something as ethereal as differentiated service code point values? So again, you have all of those capabilities and all of those things in your inventory. Now, in this class, the two other solutions that we are going to have the capability is we can actually create traffic data policies. Now, a traffic data policy is a perfect way of being able to instantiate some type of application firewall. So as an example, you have a DIA. You guys are going to build a DIA next week. That's a direct internet access connection. And that direct internet access connection gives the user in our offices the ability to be able to go to the internet directly from their vEdge that's local to where they are, rather than backhaul that data all the way to a data center to go out the internet to bring it back in. It makes things much faster, makes things much more operable. However, it does expose us to a number of risks. In order to be able to leverage that, Cisco has integrated with packages like Umbrella, and also given us the native ability to be able to implement an application firewall in our infrastructure in concert with something called a zone-based firewall, or ZB zone-based, ZBFW, sorry. Zone-based firewall functionality that says, okay, this is all well and good, but because I also have the capability of being able, again, to use things like NBAR or Cosmos. NBAR is in Cisco, Cosmos is an industry standards application recognition software that Viptela used, and it only runs in vEdges. So if you have cEdges, you're not running Cosmos anywhere in your infrastructure. But my point here is that if I see traffic that is, as an example, going to a specific URL, I could block it. So I could keep customer or employees from going to like monster.com or jobs.com. Or playboy.com or whatever. I can leverage the functionality of policy to be able to not only impact all traffic, but I could actually impact specific traffic. And it's typically going to end up being a block and report or a pass and report. More often than not, like I said, it is a block, at the very minimum, just a block and no report. But again, this is going to say, all right, based on whatever tool that we have in our infrastructure, I could write a policy that says do not allow social media. I could write a policy that says do not allow YouTube. I could write a policy that says do not allow FTP. Do not allow, RDP, any number of policies that I want to create inside of the vManage I can, and I can deploy those, and I can leverage them using traffic data policies. And then if I want to go even further, I can actually use a security policy and integrate to a solution like Umbrella or any number of other solutions that are out there for hardened DNS and stuff. But one of the things I like about Umbrella is the ability to be able to deploy cloud-based firewalls. That way, if somebody goes home and they're working on our infrastructure, I can still make certain that if they have to go through Umbrella to get to our resources or through our cloud-based firewalls that we have set up, ergo, their home network isn't going to be a potential risk for our organization. Now, the only other data policy that I want to talk about is going to be a CFlow daemon policy. CFlow D. Now, CFlow is basically what we refer to in Cisco's world as net flow. And why then is it listed as a data policy? Well, it's listed as a data policy because I write a data policy to replicate those packets. So I'm going to replicate packets, and then what I'm going to do is I'm going to direct those packets towards a collector, some type of NMS workstation. Sorry. It could be the analytics. It could be just a regular role. It could be net. It could be NetFlow, or it could be a CFlow daemon collector. Again, the options are not limitless, but the options are pretty rich as far as functionality and as far as things that we do. So I wanted to walk through this from the perspective of the Blackboard, but it's also going to be important for us to be able to, again, kind of talk about this. So what I want to do, first of all, is I want to look at this from the perspective of the two types of centralized policies that fulfill different objectives in our deployment. And those are specifically the topology and the VPN membership policies. Again, a topology policy controls the route information like OMP routes, TLOC routes, and service routes. Remember, those are the three types of routes that we work with. I have a tendency to focusing on OMP routes and TLOC routes because in this class, we don't do a huge amount of redirection as far as service graphs and things like that, but understand that it is all three. So just to make certain that my notes are complete, I'm going to come in here also and I'm going to say service routes, because they are TLOC routes. I'm sorry, OMP routes. So we have service routes that fall in that equation. So that includes OMP, TLOC, and service routes that are being distributed to sites. And I can curtail what sites receive this information based on a list that I create that includes sites or excludes sites. So again, these are all the tools that I have to be able to implement this. Now, topology, the name topology implies that we're going to be deployed using restricting the total number of overlays that we're going to have in our infrastructure is the easiest and best way to say that. And we do that in order to stop those tunnels, those connections from taking place between devices. We're really using the control plane to leverage that. Now, VPN membership policies are used to control the distribution of routing information for specific VPNs to a list of sites. A typical use case for this is going to be creating guest networks that can have internet access, but site-to-site communication is going to be restricted. So as an example, if in, say, this location right here, let's say vEdge 2, which is a branch office, I wanted people to be able to send data to the internet direct. That's that DIA that we were talking about. So inbound traffic could go out DIA, and then I could protect it using any number of these traffic data tools like Umbrella, or Umbrella is not a traffic data tool. Umbrella is a security policy, not a control plane policy. So it's a solution in its own right. But I could protect it using a zone-based firewall deployment, which is technically, well, not technically, it is an actual traffic data policy. And, you know, the key point here is that data goes out and it's protected via one-way, but traffic traveling from site to site may go direct and be encrypted, or I may force it to go through, say, for instance, the hub, like what we were describing, where I could expose it to a firewall for further protection. And the whole goal about this is to just understand from a 30,000-foot view where our technologies and where our topologies are going to come into play. So again, just to reiterate this, I mean, I'm going to redraw this drawing, but I'm going to try to do it simpler, because what I want us to talk about is going to be the function and the capability of my Vsmart controllers. Now, again, we know that no matter how many devices that I have in my infrastructure, let's say VE1, we'll say VE3, we'll say VE2. we know that all of these devices are going to be physically connected to one another in some shape, fashion, or form. I'm only drawing one transport just to make certain that we're keeping this down to its most minimum constituent or most minimum constructs. Now, when we take a look at what's happening as far as the exchange of information that's going on in our configuration, bear in mind that we know, or we should know, what's happening. So each one of these devices, let me go to a wider pen. Each one of these devices is going to use a DTLS tunnel running OMP to communicate information. So right now, what I'm going to do is I am breaking this up into its two primary constituents. So when we look at this, everything that happens basically from here to here, the way the drawing is set up is data plane. And we know that inside of this data plane, all traffic is actually going to be encapsulated by default in IPsec. And we also know that we are going to, by default, get a full mesh of connections. There's a number of ways to change this behavior. I'll show you a couple as class progresses. So we know that VEdge1 is advertising routes to the route reflector. We also know that the route reflector is going to then do, oh no, I'm sorry, I keep saying route reflector because of my class. I apologize for that. But we know that the Vsmart is also then in turn going to reflect those routes, again, using OMP to these specific destinations. So again, this is all OMP. And we know that it's OMP inside of DTLS, TLS tunnels between those resources. We know the data plane is all about IPsec. So we know what's happening here is that, well, let me do it on the other side. What's happening here is that we know that WAN edge devices, in this case vEdges, or vEdge devices, are going to send routing information. That's what they're designed to do. So we're going to send routing information. Where are we sending it? To the Vsmarts. The two Vsmarts that we're going to form neighbor relationships out of our grouping, we're going to send them information, and we're going to send it via overlay management protocol. And we also know that the scenario here is that the job of the Vsmarts, so Vsmarts are going to learn OMP routes by VPN, and we also know that they are going to redistribute or inject OMP routes by VPN. And remember, when I say OMP routes, I'm talking about V routes, PLOC routes, as well as service routes. What is different in this scenario that is different than anything that we would do in traditional or normal routing is the fact that the exchange of information between routers doesn't happen anymore. This does not take place in our infrastructure. In a SD-WAN infrastructure, the WAN edges do not exchange prefixes. They do not exchange prefixes of any kind because there is no control plane construct between them. Because what we're doing, everything that we have from here up in this drawing, and technically that would be from here up to the Vsmart, is what we refer to as our overlay. And our overlay relies on OMP plus the Vsmarts for its control plane. So this is why when we write policy in a centralized fashion, that policy is going to be pushed to and enforced on the Vsmart. And again, remember, the policy that we're going to implement is going to be directional. In other words, I can implement policy inbound or I can implement policy outbound. So let's look at that. The object here is if I were to come up here and write a policy that says I did not want to accept routes inbound from VE1, then there is no way possible that the Vsmart could ever reflect that route. So in other words, I basically did the equivalent of a distribute list. I blew that route out of the water. It doesn't exist. It was never learned by the Vsmart. Ergo, it can never be advertised. And if it can never be advertised, it can never be leveraged by any other device in the infrastructure. In fact, the only place that that prefix will ever exist is where it is going to be a local or direct connection on the given device that is its source or point of origin. Now, if I change that rule, if I come in here and instead of saying I want to filter this prefix, but I'm going to filter it out to this site right here. So I'm going to filter it going down to VE3. That means VE3 will know nothing about it, but VE2 will actually have that route in its routing table. So the object of the exercise here is that if I filter that route out, somehow I need to originate some type of default or something that's going to allow me to ensure that traffic will get sent where it needs to go. And if I change my rule to say filter out the specific, however, simultaneously add a default route with the next hop of, say, VE1, whatever that would be, it would be the TLOC of VE1, and then we would resolve the TLOC for the underlying WAN IP address. But at that particular juncture, this guy doesn't know the specific route, but we don't care because we've got a gateway of last resort here that's going to basically send the data to vEdge1, and then vEdge1 could then in turn send the data wherever it needs to go. So I probably should have done that in the other direction. In fact, I will, because I filtered it coming down. So instead of saying VE1 will send the traffic to VE2, and as that scenario goes, what we'll do is we'll see that the data will actually travel from here, and from here it would travel to there to get to that destination, because as soon as it got to VE2, VE2 has that prefix. So, I mean, fundamentally, that is all that we're describing. And it all really boils down to how we handle all of these individual configurations, and that we have a firm understanding of OMP. On the first day of this class, I always tell every student that if you want to understand SD-WAN, it is absolutely critical and absolutely incumbent on you to understand OMP the way you would understand any other routing protocol, whether it's OSPF or EIGRP or BGP. And it is very, very similar to the way BGP works. And again, we've already talked about these routes that we have here. We have the OMP route, aka the V route. These routes present prefix information that the WAN edge devices will learn from their local networks. As an example, these could be connected, static routes, they could be OSPF processes, and they're going to be in-site. In other words, they will be running or being part of the network infrastructure that's connected to the VPN, like VPN 100 here. And then what ends up happening is those routes are actually going to be communicated via OMP to the Vsmart, whereby the Vsmart starts making a record of all of those routes for that given device, and the network layer reachability information will resolve to the TLOC of the device that originated them. We can see these prefixes by executing the show OMP command. Show OMP route, show OMP TLOC, show OMP services. The second type, like I said, this is a prefix. and it will resolve to an NLRI that we call a transport locator, which again is going to be the system IP, color, and encapsulation type of the originating device. That becomes learned by the OMP, via OMP on the Vsmart, and then obviously it's going to get reflected. T-lock routes. These routes are designed simply to carry T-lock information from V-edges to Vsmart controllers. And you can actually see the output if you use the show OMP T-locks command. But ultimately, the job of the T-lock is to take the T-lock route is to take the T-lock, which is going to again be the system IP, the color, and the encapsulation type, and translate that to a WAN IP that I can use to resolve reachability so I can actually forward a packet across my IP transit. Now, service routes, we don't really worry about them too much in this class. I do have a lab that will have you implement a firewall, and we'll take VLAN 10 and VLAN 20 and stitch VLAN 40 into the data path using something called a service graph. And then what we do is once it goes through VPN 40, it's traveling across the firewall, which is an ASAV in our lab. Now, service routes are used to represent specific network services, like the firewall that I described, or say, for instance, an intrusion prevention system that are going to be running in sites to which edge routers are going to be connected. And again, if you want to see those, you just execute the show OMP services command. But they are designed basically to advertise services. And those services, for the most part, would be things like firewall or IPS. And there are advanced IPS functions inside of the environment that we can manipulate also, again, using security policies. Now, I want to spend just a minute on this, and then I'm going to open up for any questions and give you guys a break. I've been talking for a long time. I realize that. So when we start looking at our infrastructure, we have our Vsmart controllers. Now, we know that in a production environment, we're going to have at least 3 of these puppies. So let's say Vsmart 1, Vsmart 2, and Vsmart 3. We also know that these devices are going to form OMP peerings with each other, which means they're going to have DTLS tunnels between them with OMP running in them. Should have used green since it's what I've been using. OMP, 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 where this is a DTLS tunnel. TLS tunnel. And we know that they implement and handle all of the control. And their job is to formulate a routing table. So the job of these guys is going to be to create a routing table based on the information that's being advertised to them via OMP from devices that exist in my infrastructure. So if I had 4 devices, and we'll just go ahead and call these V-edges. We know that these devices are going to be connected some way to get information between all of them. And we also know that we call this connection right here, this is going to be our overlay fabric. And we know it's going to be comprised of IPsec tunnels. We also know, and I'm going to pretend to divide this in half. We also know that these devices are going to send OMP updates, and that's how this database gets refreshed or propagated or formed. We also know that the job of the OMP configuration is also to allow this information to get redistributed. I just split it in half. Obviously, all four would be communicating, and again, all four would be receiving data and updates unless I implemented a policy. Now, we also know that the job of this is going to be, since it is OMP, and we know that an OMP translates to what we call a V route, we know that the NLRI, network layer reachability information, is going to allow us to be able to create a T-lock table. So everything that we're going to have, a prefix or whatever, is going to translate to a T-lock, and then I'll look up the T-lock destination in the T-lock database. So I've really got two databases here. I actually have the routing table, the OMP VRoute routing table, that translates to the the NLRI, which translates to a T-lock, and then I have the second database, which is going to be the T-lock table, which is going to be comprised of my OMP T-locks, T-lock routes. Actually, they're more accurately referred to as T-lock paths, but it gets kind of confusing. So again, the thing that you've got to understand, that there are going to be instances. Let me use this as a, I'll use the pink color. So it becomes important for us to keep in mind that there are going to be instances where we are going to have data that is going to be inbound, and also at the same time we are going to have data that is going to be outbound. Now, if I want to impact any one of these, what I would do is if I wanted to impact what I was learning, I would actually implement an inbound policy. And if I was going to impact what I choose to advertise out, I would be utilizing an outbound policy. So the tools that we're describing here are all centralized policies. So centralized policy is going to be written against and enforced by the Vsmarts. And again, it's going to be interpreted as inbound or outbound. Now, I need you guys to understand that there are some key, important, and fundamental rules when it comes to centralized policy. The first of those rules, let me change to white because that'll show up better. I don't want there to be any misinterpretation here, and I'm going to go to a bigger print. The first rule is these policies are never pushed. Policy is never pushed. In other words, I write the policy and I apply the policy to the Vsmart controllers, and that policy is never pushed to V edges or C edges. I should be using the letter W edge, but I bounce back and forth so much that it gets confusing for me and for students. So, like I said, the policy itself is never pushed to the V edge routers. However, only the results of the control policy are going to be advertised. So in other words, the policy is never pushed, but the results will be visible, I guess is the best way to say that, on the V edge. So just for clarity's sake, one more time. The policy itself is never pushed to the V edge routers. Only the results of the control plane policy are advertised to the V edge routers, and that gets advertised via OMP. So what I'm getting at here is that if I wanted to look at a centralized policy on a V edge, I can implement a command or execute a command that's going to let me show policy from Vsmart. But if I type show run, I'm never going to see that policy in the running configuration of the device. And like I said, that can get pretty confusing when we start looking at the way the infrastructure works and when you're troubleshooting. Because sometimes, I mean, we're of the mindset that we should always do a show run and look at the running configuration. But when it comes to a centralized control plane policy, the key thing to keep in mind is that policy, the actual policy itself, is never pushed to the V edges. Now, what that's saying is it never will appear in the running configuration, unlike a localized policy. So the results will be visible on the V-edge, and it's interesting to note that the Vsmarts will actually push the results of the configuration, but it will only be in running memory. Show runs not, that's not even a good, it's going to be memory resident, I guess is the best way to say it. So it's going to be in the RAM somewhere, but it's not part of the configuration parser. So if you want to see these policies, you have to actually implement show policy from Vsmarts, and it will query that specific story location in the memory run space and produce the results. So you can see what was applied on the Vsmart that would be affecting the traffic. And the results obviously will be visible on the V-edge. If you are trying to stop it from learning something, obviously that route will not exist, or it won't appear. Now, in order to be able to address this, we need to talk about default Vsmart behavior. Now, there are no centralized control plane policies configured in the vCenter by default. None, zip, zilch. They just simply don't exist. And therefore, by default, there's going to be a number of specific behaviors that we need to make certain that we understand. And then once I cover these, I'll give you guys about a 15-minute break. And when we come back, I'll wrap this part out. And I'll actually, before I even go here, are there any questions about what I've covered thus far? You guys, I don't know if you're dead, alive, or asleep or whatever. So I haven't heard anything from anybody. I feel like I'm talking to myself, which pretty much have been doing all week. So are there any questions about what I've discussed thus far?
No, that was the interesting stuff. That's the reason we are just listening.
Okay. Okay. I didn't know if I was actually, last night I was accused of giving the class an aneurysm because they couldn't absorb the information at the rate it was coming. So,
But we
all right.
love have a break.
Okay. Well, let's go ahead and take a break, and then when we come back, I'll talk about the defaults, and then I'm going to talk about the application of said policies, and then what we'll do is we'll get into some labs. Your equipment will be turned off. I had to shut the labs down for my night class, like I was describing. So if you guys want, you can go ahead and log into your pod and make sure get everything turned back on, and that way everything will be working by the time we get in. So let's go ahead and take about a 15-minute break. I know I'm suffering from diarrhea of the mouth here. So it's been, like I said, it's been a long week. I went to bed with my throat was very sore last night, but we'll take about a 15-minute break. And when we come back from that break, I'm going to wrap this up. And then this is one of the reasons, because I didn't want to go into localized policies because we got to go so deep in centralized. So I'll see everybody back here in about 15. All right, I realize that this is brutal, but there is a lot of stuff that I want to make certain that we cover, and I want to make certain that you guys understand. So, what I want to do is I want to talk about filtered or policied and non-policied behavior. So, we're going to call non-policied behavior default. So, what I want to really discuss is what Vsmarts do by default. So, their behavior. And then what I want to do is I want to talk about what we can do with centralized policy. Now, the law of the land here is the same. So by default, we know that we're going to have our Vsmarts. So Vsmart 1, Vsmart 2, and Vsmart 3. And we know that those Vsmarts are going to be representative of our entire control plane. And when we have no policy configured, which is the default operation, default equals no policy. I'll just do an arrow there. So by default, we have no policy implemented in our infrastructure. The rules are for us. Again, remember, these resources are going to create the idea of OMP routes, TLOC routes, and the role of the system, again, with no policy, is going to be that the Vsmarts are going to receive the information coming from our hosts. So again, let's say I've got vEdge 1, I've got vEdge 2, and I have vEdge 3. We know that they're connected via some transport mechanism, just like what I'd illustrated before. And we also know that by default, we are going to receive information from all of our vEdges. And the default behavior in this instance is going to be to accept all routes. And you guys have seen this done in your lab. We accept all routes coming from all of these devices, and we inject those into our table. So again, this is just representative of the total configuration in here with regard to the routing table. And again, remember, this is implemented on a per VPN basis. Now, remember, all this information is going to be sent from all sites regarding vRoutes, TLOCs, and service routes towards the controllers using the DTLS control connections that are represented here by these green arrows. And we know that inside of every one of these, I am running OMP. And we know that by default, we're going to accept all routes. Well, it should stand to reason based on what we've seen. I'm going to change to a different intensity of green, or I'll use yellow. We also know that we are going to reflect those routes to all of these devices. And again, what that translates to is, once again, like I said, we are going to, should have used white, redistribute all of those routes. Now I say reflect, but it's basically the equivalent of redistribute. But I don't like that word because it makes it sound like redistribution, and it's not. So you will always hear me use the terminology of reflect. And the other thing is this helps me teach topics like SD-WAN to people who have an understanding of the way protocols like BGP works because they are so familiar. So, man, my handwriting is atrocious this morning. I mean, worse than normal. So it's going to reflect those routes out. And then those routes are going to end up getting installed in the routing tables on these devices. And then by virtue of the fact that we have a uniform deployment of resources with regard to the exchange of all of this information, again, using OMP, we have this exchange. Now, I don't want you to think that there's a separate tunnel for receive and send. I'm basically saying we're going to learn all the prefixes via these DTLS tunnels, and then we're going to send the information out via the same DTLS tunnels. I'm not trying to give you guys with the impression that the implementation looks like it's drawn here. I'm just trying to keep the two trains of thought separate, the receive side and the reflect or the redistribute side. Now, when we start looking at this, like I said, the Vsmart controller by default with no policy is going to accept all incoming routes. That includes all three routes. That's OMP, TLOC, and service. It's going to store them in a respective routing table set up per VPN, so on a VPN basis. The Vsmart then will redistribute all learned routes to all WAN edge devices in the infrastructure. This is going to result in, by default, a full mesh of connections using those IPsec tunnels that we've been talking about. And it's also going to include what we refer to as full IP reachability. Now, in class, you guys have seen some IP reachability conditions called partial. Now, bear in mind, without policy, we would have partial connectivity because of, say, a configurational problem, like leaving a default route out for the second connection or something like that as it relates to the lab. And it's also possible to filter policy in such a way that you can accidentally induce partial IP reachability in your infrastructure, again, because you're filtering it from one specific and you're not filtering the others. So again, it's something that you're going to have to look at, because anytime you implement policy, what you're saying you're going to do is you want to implement oversight. Now, like I said, it's going to be the job of the Vsmart to reflect or redistribute those routes. And it's also very important to understand that we still have a finite state machine. A finite state machine is like when I bring up my neighbors in OSPF, the formation of the neighbor adjacency, transitioning from initializing to two-way, to exchange start, to exchange, to loading, to full in a unicast environment with OSPF. That's the adjacency state machine, the formation of those neighbors successfully. Once that happens, then what we do is we rely on the finite state machine, where we use those same hello messages as a heartbeat to ascertain or to assure that our adjacent device and resource is still alive. Well, inside of SD-WAN, the finite state machine means that once we've got this configuration in place, vEdges will actually continually send updates. vEdges will update OMP information continuously. And by virtue of the fact that the edges are going to update OMP information continuously, it's going to be also important to understand that as a result of this, the Vsmarts will constantly update the database. That will either be update or refresh the entries in the database. And what's going to end up doing is it's going to do this based on each update. And then if something does change, that's going to trigger a new operation to reflect the changed information to all of the devices in the infrastructure. So what we have here is we have a single pane of glass for a unified overlay control plane. All of these things working together ensures that everything is updated and organized and constructed. properly and functioning the way it's supposed to. Now, one of the things that we may have to acknowledge out of the gate is this might not be something that I want to have happen. Imagine that analogy where I've got like the United States, and let's say I have Australia, and in the United States, I have 3 sites, and in Australia, I have 3 sites. And the issue is that right now, that means that this site will form a peering with this site and with this site. And because of the full mesh rule, it's also going to form a peering like so. Again, alluding to this principle of full mesh. And that may or may not be something that I want to allow. In fact, more often than not, most organizations that have infrastructure like this is going to have a dedicated pipe between, say, 2 regional headquarters sites that's going to be what we would refer to as a fat pipe. High bandwidth, high throughput. And what they might want to do is they may choose to set up an infrastructure where these devices are connected like so, and data between regions will actually need to translate the local region along that fat pipe, where we can spend money and make certain that we've got the ample bandwidth to put the infrastructure in place. This would be something that we would implement with a topology policy. So again, centralized control plane policy. As an example, we need to talk about how that would get reflected and how that would actually be deployed. And it's really not hard. Now, what I'm going to do is, rather than redraw all of this, I'm going to go to an orange pen. And what I'm going to do is now the default was no policy. And anything that I'm going to put in this orange is going to be with policy configured. So with a policy configured, if I create a policy and that policy is inbound, the thing that we're going to have to understand is that only accepted routes will be inserted into that routing table. The policy, if left by its default, will be a reject all. So it's going to reject all by default the moment I apply that policy, which means zero trust. So what I've got to do is I've got to say what I want to accept or change the default behavior. So I could block specific things and then accept everything else. So you can reverse the logic. When it comes to the outbound direction, the redistribution in the outbound or the reflection in the outbound, again, it's going to be only accepted routes are going to be redistributed. Again, this is all via OMP, Overlay Management Protocol. And by default, it's going to be reject all. So if you apply a policy, an empty policy inbound, you're going to stop all learning. If you apply an empty policy outbound, you're going to stop all learning. The very second that you apply those policies, what you're saying is that when a centralized policy is going to be applied in an inbound direction, it filters or modifies the routing information that's coming from the V edges before it can ever be placed in the routing table. So think of an inbound centralized policy like a distribute list. Secondarily, when a centralized policy is going to be applied in an outbound direction, it filters or modifies the routing information that's going to be advertised to the V edges. Now, as a result of this, I can be selective. I could choose to advertise it to everyone, but if that's the case, then why even use a policy? Just leave it as is by default. But if I wanted to only advertise information to key resources, so as an example, imagine the situation here where I have that regional HQ in the US, and then I've got that pipe out, my fat pipe that goes to Australia, and I've got my physical connections here. I would never, ever want this device to communicate directly to some device in Australia. I would want everything to go through the headquarters office. So what I would do is I could write an outbound policy that says, don't advertise any of this information about Australia to these two sites. Block it. Then all I got to do is say, well, you advertise this one. This one's a good to go. And then I could stimulate or create that default route, that quad 0 route, to send information to here so I could get information delivered, but I want to block the ability to be able to form IPsec tunnels, say between, middle of nowhere United States to middle of nowhere Australia, which is, I think, pretty much anywhere other than Sydney and Melbourne, because, even in Canberra, the internet was terrible. So the point being that the policy is going to be the way that we're going to implement this. Now, this class isn't all about theory, obviously. This class is going to ultimately be about trying to build this infrastructure and set up a working lab environment. Now, what I want to highlight here is that the beautiful thing about SD-WAN centralized policies, is they're very much like modular quality of service CLI, or what we would refer to as hierarchical queuing framework. Now, in these constructs, we've had them for years in Cisco. Modular quality of service predating hierarchical queuing framework, primary difference being, among many other smaller differences, modular quality of service CLI has a single priority queue, where hierarchical queuing framework could have two, and in some instances even more, depending on which vendor you're integrating with. But the thing that we've got to keep in mind here is that we have this approach inside of modular quality of service CLI, or MQC, whereby what we do is we match on traffic. Actually, we don't match. We classify first. We classify traffic. Then what we do is we match on that traffic. And then based on the matching, we take an action. And then what we do is we apply this. So we've got a class map, a policy map, and then a service policy. So it's a three-stage deployment mechanism. And it's very similar when it comes to policies in the vManage. So in the vManage, we have what are referred to as vManage policy components. And there are three. Technically, they're not even really three definitions. There's three steps. So in modular quality of service CLI, we go in, we match, we will write the policy, and then we'll apply the policy. That's basically what it distills down to. Well, in the vManage, the very first thing that we're going to do is we're going to create groups of interests. So create a group of interest. Now, like I said, at Cisco IS, there are a few types of lists that we can use to identify traffic. Route maps, prefix lists. Like I said, there's a number of things, and we all should be familiar with them. So, just the most basic: access lists, prefix lists, AS path lists, community lists. We've had lists for a long, long time. In the Cisco SD-WAN, there's even more types of lists, and we're going to talk about those. But right now, what we do is we create a group of traffic, a group of interesting traffic, by utilizing the principle of creating lists, VPN lists, TLOC lists, site lists. Then the next thing is, obviously, remember, this is a centralized policy. And we said a centralized policy is made up of two parts. Well, that's where we see these. We are going to then, based on interesting groups, we are going to configure topology and VPN membership configurations. Now, this specific test, this specific step, what we're going to do is we're going to define our control and VPN membership policies. These are all policies that we're going to use to manipulate the propagation of routing information. And specifically, this is going to be inside of the control plane, which means we're going to use these to manipulate OMP prefixes and TLOCs. Now, again, service routes goes in there too, but that's not what we're focusing on right now. So when we look at this, it's going to allow us to be able to propagate routing information in the control plane regarding OMP and transport locator routes. Now, a control plane is going to be defined as a sequence of match action statements. Now, typically, we'd create a list in step 1, and then what we're going to do is we're going to match based on the steps that we took in that we made in step 1, and then what we're going to do is we're going to apply whatever that action is. That action could be drop. That we would use the word reject in Viptela, or we could permit, or we could change a value. As an example, if I wanted to send the data to another hop, I could change the TLOC, but like modifying the next hop address in BGP. There are a number of different options that we can deploy. Now, we're going to talk about those. But the third step in all of this is going to be, at this point, we need to apply the policy. So this is kind of like our service policy. So we apply the policies that we're going to create. Now, we apply those policies specifically to sites and VPNs. Remember that second value, that VPN membership that we were talking about that was right up here? That's how we delineate or denote the VPNs that we're going to leverage our policies against. Now, it becomes really important for us to take a look at this principle of centralized policy. Centralized policies will have a name. So we'll name the overall policy, and it's going to have a description. Like everything else in Viptela, the description and the name are mandatory. Again, I'd like to beat the living daylights out of the guy that came up with that idea. But following this three-step configuration, notice that I have lists, and then I have policies, and then what I'm going to do is I'm going to apply my policies. That is the order of operations that we're going to follow. So centralized policies will need to be named and have a description. We know that we will need to create lists. Once we create our lists, what we're going to end up doing is we are going to define our policy. Once our policy is defined, what we're going to do is we're going to apply our policy. Those are our 3 steps. Now, starting at the left, let's talk about some of the tools that we can use. Not all of them. The ones that I want people to know very well. The very first one is going to be a site list. Am I going to write a policy that's going to affect data being learned from a site, or being or the policy of information being advertised or reflected to a site? I can manipulate things based on prefix lists. Data prefix lists. A data prefix list says, oh, well, I'm learning a prefix about like 8.8.8.8, just as an example, and I don't want to learn it. I could write a prefix list that would match that value, and then all I got to do is define a policy that says accept or deny that traffic. Another one, and probably the one that everybody gets the most familiar with, is going to be a VPN list. A list of VPNs. So I might want to create a hub and spoke topology for VPN 100, but allow VPN 200 to be a full mesh, whatever the requirements are. Also, I might want to look at traffic coming, say, for instance, from a specific T-lock or group of T-locks. I can create a T-lock list. And that's other stuff that we can do, but I'm not worried about anything else beyond that scope. Now, once I've created my list, what I want to do is I want to aggregate my lists into a set of logic. And it's also important to understand that just like the centralized policy itself, my policy is going to have a name, and it's also going to be a requirement to assign it a description. So when it comes to the policy, there are going to be a number of things that I need to worry about. I need to understand what I'm going to do, aka what's my default action if I do nothing. And I also want to implement an order of operations. So when we start talking about defining policy inside of the context of the vManage, it's very similar to route maps. So what I'm going to do is I'm going to specify a sequence of operations. And then what I'm going to do is at the end of that sequence of operations, I want to define whatever my default operation is. And remember, by default, my default information is going to be reject, my default action. So I only have two choices here. It can be accept or reject. And if I leave it as is, it will always be reject, just like I mentioned in the previous part of the lecture. Now, when I can create a sequence of actions, and for every sequence that I could create, what ends up happening is I have the choice of matching on something and then taking an action, whatever that action is. And that action will be definable in the policy that you're creating. So I could have multiple sequences. I could have sequence 1, match on X, do Y. I could have sequence 2, match on X, Y, do X. And then if I have nothing else, it's going to be whatever my default action is. A lot of times I'll specifically deny something or specifically deny a group of things and then accept everything else on the tail end of my default action just as a way of having my catch-all in place. But by default, this is going to be a zero trust style implementation. So once I've created my policy, which is going to be combined of a number, one or more sequences in which I match and take actions, then what I'm going to do is I'm going to perform whatever my default operation is. Now, after that, what I'm going to end up doing is I need to apply that policy, and we've already talked about this. The application of this policy is going to either be done inbound or it's going to be done outbound. Inbound and outbound application of the policy is paramount. However, just because we've done this, because we've created this policy does not mean that this policy is doing anything. In modular quality of service CLI, it's a guarantee that we know that we have to classify our traffic. We can create our policy matching and then taking an action. So match a prefix list. If it matches this prefix list, drop this traffic. The last statement and the end is going to be a deny all by default unless I change the logic. Very similar to what I just described. Now, when I create a service policy on an interface, inbound or outbound, the moment that I create the service policy, the policy goes into effect on the interface. However, that's not the way that it's going to work when it comes to the vManage. So we have our vManage. This is the graphical representation of a vManage. And what we do is we're using that vManage in order to be able, and I'm going to try to do an approximation of a Vsmart here. We have a Vsmart, and this is representative of our entire Vsmart cluster. Now, understand that we are going to use the vManage GUI, graphical user interface, or UI. And what we're going to do is we're going to employ the policy wizard to create whatever policy it is that we need in our infrastructure. And then that policy is actually going to be deployed when that policy is activated. So what I'm getting at is I could have several policies, but only one centralized control policy can be active at any given time. So if I want to do a whole lot of stuff, if I want to implement lots and lots of different policies, I have to aggregate all of those policies into a single control plane policy that I can then activate that would contain all of those constituent configurations. Now, when I create that, the centralized policy, that policy itself, it is pushed to the Vsmart. And it's pushed as a netconf transaction. Now, obviously, when I push it, understand that since it's pushed, that means it's going to show up under the policy configuration inside of the CLI. So in other words, it's going to show up in the show run. So the moment that it's activated, it's pushed to the Vsmarts, all the Vsmarts. So my case, it would be 3 for the topology that I'm discussing. And then it's immediately going to appear in the CLI. So it's going to show up in the running config of the Vsmarts themselves. Now, it is important to understand that that information is then in turn going to get disseminated to all of my vEdges, vEdge 1, vEdge 2, vEdge 3. And like I said, the information is going to get pushed to each of these devices. I'm sorry. It's not pushed. I apologize. It's never pushed to the vEdges. So the OMP and the OMP configuration, these are OMP updates. So whatever the control plane settles on is going to have to be communicated to the vEdge. As a result of this is what I was saying when I said that we could see it on the vEdges as a result. We can't see it in the running config. So since it's not pushed, there is no CLI impact. However, you can say show policy from Vsmart, and what it will do is it will give you the listing in its operational RAM. So in other words, it's going to produce the results from the runtime information, not from the running config information. Now, like I said, I know I've gone over a whole lot of stuff here, and I gave you guys a guide in your Dropbox that covered the basic functionality of how these constructs work for us and what these constructs do with regard to the way that we can affect and manipulate things. Now, what I'm going to do next week is I have promised, I hit 6,000 subscribers on my YouTube channel. So for a guy who thought he'd get 10, that's pretty good. And what I'm going to do is I'm actually going to release 6 videos that cover the fundamentals of all of the centralized control plane policies. So I'm going to try to record those videos, or at least some of those videos, next week, and I'll make those available to you guys. Also, I'll put them in the Wistia site. And what I want to do is I'm going to take the theory that I just walked through, and I'm going to go through a lab where I'm going to build a hub and spoke that's going to restrict the formation of spoke-to-spoke tunnels. I'm going to build a hub and spoke that's going to allow hub-to-spoke routing. I'm going to build one that a hub and spoke that's going to enable spoke-to-spoke communication. So in other words, a partial mesh. And then what I'm going to do is I'm going to do some traffic engineering specifying TLOC preference. And then I'm going to do one about end-to-end path tracking. And then I'm going to do another that's going to cover how I can set up VPN membership policy isolation for guest users. So if you log in and you're a guest, then you would be stuck in a specific location, so I could restrict access. So the plan is to churn out those videos, because I think those videos would be good for the website, a way of being able to celebrate it, but it's also going to be something that would be useful for you guys. Now, in your lab guides, you have labs that are far more complicated than the labs that I'm talking about doing. In your lab guide, you have a regional hub lab, like that is the equivalent of the lab that I illustrated with the site in Australia and the site in the United States, where we take one of the branch offices and we pretend that we want it to not be able to communicate direct. So it's not like that you guys don't have those labs. I just wanted to come up with something a little bit more simplified, because some people I've noticed are having difficulty visualizing what's happening in that larger lab. So I figured if I broke up the task to be able to implement control plane policies in some smaller demonstrations, then it might make things make more sense. So the other thing too is that a lot of this stuff is like the first time a lot of people have seen it before. So I did want to make certain that we go over all of the fundamentals. And really and truly, it boils down to this: the lists, the define policies, and the apply policies.